Hello, dear students. This is Yash Kumar Gupta, and I teach maths and physics for classes 11th and 12th. I really like helping students who are struggling with the concepts, who want to know actually that what is going on, why is it going on, and who are curious to know the things as they are. So, without further delay, we can start learning now about mathematical induction, the principle of mathematical induction. In this very short session, we will see we will get a basic idea of this principle, that how does it work, with an example. Okay, with a quick example, let's start this one. So we are going to learn a very powerful mathematical technique today. This is called as the principle of mathematical induction. Mathematical induction. So before we start learning the formal definition of PMI, which is principle of mathematical induction, I want you to imagine a row of 100 dominoes standing one after another. Somewhat like this. Okay. And so on. 100 of them. So what happens when one of the domino falls, like the first one, if it falls on the other? It will push the next one to fall down, which will push the next one to fall down, and so on. And thus the last domino will also experience a push and will fall down eventually, right? That is what the principle of mathematical induction all about. So whenever in maths we have to prove a statement that is true for all natural numbers, we generally perform two steps. Step 1. Step 1 is that we verify that the statement is true for the first value, or known as the base value. Verify for the base value, which is usually n equal to 1, or it can be different also, maybe n equal to 2, 3 or something, depending upon the question. This is exactly like pushing the first domino. Now comes the step 2. Step 2 is the induction step. Okay. So we assume that the statement is true for some n equal to k. Because as we have already proved that there exists some n for which the statement is true. That could be the base value, that is n equal to 1 or n equal to 10 or anything. But there exists an n for which the statement is true. So that now we can assume that the statement would also be true for some n equal to k. Maybe that k is the base value itself, or it can be anything. So assume that statement is true for n equal to k. And then how do we induce this hypothesis? Is by proving that statement is true for n equals to k plus 1. So what does it mean, my friends? It means that for every n equal to k, if the statement is true, it pushes the statement to be true for n equal to k plus 1 as well. Okay. So for, let's say, if the statement is true for n equal to 1, it pushes that it must be true for n equal to 2 as well. Okay, because we have assumed that it's true for n equal to k, and that this implies this. So if n equal to k is true, then n equal to k plus 1 would also be true. So the statement to be equal to n equal to 1 pushes it to be true for n equal to 2 as well, which further pushes it to be true for n equal to 3 as well. Okay. If the statement is true for n equal to 2, it pushes the statement to be true for n equal to 3 as well. If it is true for n equal to 3, it pushes the statement to be true for n equal to 4 as well. So this is the induction. Like if this is k, this is k plus 1. Then if this is k, this is k plus 1. Then if this is k, this is k plus 1, and so on. Right? Now let's understand this thing with a simple example. Have you ever thought what is 1 plus 2 plus 3 plus 4 up to 100? Or why 100? Have you ever thought what is this up to any n? Let's say up to 1000, up to 10,000, up to 256, up to 998. We say, I mean, you might have seen this famous result that it comes out to be equal to n plus 1 over 2. You can prove this using AP you might have learned in 10th standard, but can we prove this statement using principle of mathematical induction? Let's see. So the question is that prove this statement using PMI. PMI here stands for Principle of Mathematical Induction. So what is the first step? First step is prove that it is true for n equal to 1. Or let's check for the base value. So for n equals to 1, our left hand side, n stands for number of terms in the left hand side, okay? So left hand side would be 1 because there is only one term, which is 1 itself. And for n equal to 1, the right hand side would be 1 into 1 plus 1 over 2, which again comes out to be 1. So we have LHS equals to RHS. Hence we can say that statement is true for n equals to 1. The next step, the induction step. Let's assume that, assuming that statement is true for n equals to k, which means that we are now stating 1 plus 2 plus 3 and so on up to k is equal to k plus 1 by 2. Let's mark it as equation 1. Now using this result, we have to prove that it is true for n equals to k plus 1 as well. So now checking for n equals to k plus 1, whether the statement is true for or not. So let's see what is the LHS if we put n equals to k plus 1. So LHS would be 1 plus 2 plus 3 and so on up to k plus 1, right? Now we know that the term just before k plus 1 would be k. Okay, so I'm writing this term, and now we know that this thing is actually equal to this thing from equation 1, right? So using equation 1, we can say that LHS is actually equal to k plus 1 over 2 plus k plus 1. Okay, using equation 1, we have stated that. Now you already know how to take LCM. So it would be k into k plus 1 plus twice of k plus 1 only. And now we can take k plus 1 as common and we have k plus 2 over 2, which can be further written as k plus 1 into k plus 1 plus 1 over 2. Do you remember our n was k plus 1 itself? So it is like n plus 1 over 2. It means the statement is true for n equals to k plus 1 as well. So this is equal to the RHS for n equal to k plus 1, right? Hence we have proven that statement is true for n equal to k plus 1 if it's true for n equal to k. Hence the statement is true for all n equals, or for all n belonging to natural numbers. This stands for the set of natural numbers, and hence how we can prove this using the mathematical induction method, as you can see here. Now, this method is useful to prove inequalities as well. As you learn it further, you will explore that not only equalities, but using the same principle we can prove so many inequalities as well. It is helpful for so many modern proofs. And PMI is one of the most important proof techniques in mathematics. You will find it to be frequently being used to prove formulas involving sum, divisibility, inequalities, and various types of sequences. So the entire method is having only two steps: verify for the base value and then the induction step. This is it for now. Hope you understood the concept and the intuition behind it. So thank you very much for giving your time, guys. I hope this gave you a glimpse of how we'll approach maths in our regular classes. Thank you.